we can revisit Green's theorem and take a look now at different vector forms of the same theorem. Now, the curl and the divergent operators actually allow us to rewrite Green's theorem in versions that will be useful a little bit later on in the semester. Now, let's suppose that the plane region D, it's the same D we've been dealing with before, and its boundary curve C, and the functions P, Q, and R all satisfy what we need for Green's theorem. So, in other words, what we need is we need curve C to be positively oriented. Piecewise smooth, simple closed. I'll go ahead and write those down as reminders. See what else we need. We need D, the region D, to be bound by C. So C is a curve that goes around D. So I have see P and Q have continuous partial derivatives on this open region that contains D. And then what we get from Green's theorem is the line integral P dx plus Q dy can be written as the double integral over the region D of the partial of Q with respect to x minus the partial of P with respect to y with respect to the area. So let's consider this vector field F equals Pi plus Qj, and its line integral is going to be the integral over the curve of f dot dr. There's nothing new here. I'm just reminding you of a few things. So we make some connections. Now, if we think of f as a vector field on R3, we can simply let z equal 0. So if we do that, what I'm going to end up with is p of xy. I'll have q of xy. And actually, I probably should write that as x, y, z. But anyway, it's essentially going to be x, y because z is just going to end up being 0. So if I think of the curl of f, let's see, I'm going to have the partial with respect to x, partial with respect to y, partial with respect to z, I, j, k, and then p of xy, I'm just going to write as p, q, and 0. Now, when I go through all this, because of the 0, what I end up with is a partial of q with respect to x minus the partial of p with respect to y, k. The I and j components are actually 0. Therefore, the curl of f dot k, this is the curl of f, so I'm going to take all of this and dot it with k, is going to equal the partial of q, partial of x, minus the partial of p, partial of y times k dot k, which just gives me the partial of q, partial of x, minus the partial of p, the partial of y, by what the dot product does. Therefore, what we can say is that this integral, this line integral over the curve, f dot dr, is equal to the double integral over d of the curl of f dot k dA. Now remember, when we've been dealing with the line integral, we've been dealing with the tangential component of the line integral. Actually, I shouldn't say of the line integral. It's a tangential component of the vector field along that path C. So this actually expresses the line integral of that tangential component of f along C as the double integral of the vertical component of curl of f over the region D enclosed by C. When I said vertical components, that's because of k. That is z. So what we can do now is actually define a similar approach which involves the normal component. So we take a look at a similar approach involving the normal component. So if C is given by r prime of t equals x of t I plus y of t j, let's say a less than or equal to t less than or equal to b, then the unit tangent vector is x prime of t, x prime of t over r prime of t, actually the magnitude of it, plus y prime of t, I need I right there, over the magnitude of r of t, or r prime of t, j. And that's just a reminder of how we define the unit tangent vector. So what I'm thinking of right now, in terms of x and y, I'm going to have this curve C in the region D. So at any point along this curve, I'm going to have my unit tangent vector and the vector normal at that point. Now, you can confirm that this normal component is going to be y prime of t I over r prime of t, magnitude of it, minus x prime of t j over, again, the magnitude of r prime. So with this, we can see that the line integral over C of f dot n ds is equal to the integral from a to b of f dot n. I'm going to add this. That's not multiplied by t, that's of t. Yeah, f dot n, both these are functions of t, times the magnitude of r prime of t dt. And now I'm just going to do a little bit of manipulation with this, and we can get a couple different forms out of it. This is actually going to be equal to the integral from a to b. Remember, p now is a function of x of t, y of t, c times y prime of t, divided by the magnitude of r prime of t, minus q of x of t, y of t, x prime of t, here we go, x prime of t, divided by the magnitude of r prime of t, dt, which is equal to the integral over the curve of p dy minus q dx, which is equal to the double integral over that region D of the partial of P with respect to x plus the partial of Q with respect to y dA. But notice this very last integral here. This is nothing more than the divergence of f. So what I can do is I can rewrite this into yet another form, which could be useful. I can say that the line integral over the curve of f dot n ds is equal to the double integral over the region of the divergence of f of xy dA. Now, just to make sure you didn't get lost in all of this substitution and rewriting and stuff, what is this really saying? What's the purpose of this? Well, we've been dealing with, like I said, the line integrals of the tangential component. So what this does is this gives me the line integral, go back to my diagram here, of the normal component to the curve. So what this actually says is, let me write it down for you. This says the line integral of the normal component of the vector field F along C is equal to the double integral of the divergence of F over the region which we defined as D, which was enclosed by this curve C. So that's actually kind of cool.